Welcome to your CCPS Science Review Lab. I've got a puzzle for you today. What you're looking at is a balance, and you can see that on either side we have maybe seemingly two different types of material, but yet they appear to balance. Can you figure out my puzzle? How is it that the mass on both sides of the balance are equal? Well, if we count up the circles on the right-hand side, we've got 1, 2, 3, 4, 5, 6, 7, 8. On the left-hand side, we have 1, 2 circles and then 2 squares. If you've thought about it and you've come up with the idea that each square is equal to 3 circles, then you're absolutely correct. If we were going on the assumption that the mass of one square is equal to the mass of 3 circles, then that would be like for this square, 1, 2, 3 circles, and then 4, 5, 6, 7, 8 circles, which is exactly what we have on the right-hand side, and then they balance. I find this is a very good segue into talking about the laws of conservation of energy and mass. So let's focus on the law of conservation of energy, first of all. When we think of conservation, lots of times we think of environmental conservation and saving the environment, respecting it, preserving it, if you would. Okay, and if we look at it from that perspective, because we don't want to lose the environment or we don't want bad things to happen and for it to get lost, because we know that all of those organisms and the parts of our planet are really important. We can think along those same lines with the law of conservation of energy, in that nothing should be lost, okay? The amount of energy that you put in should be the amount of energy that you get out. So, for example, if we look at our ice cream cone here, that represents chemical energy, and that energy is stored within that ice cream. When the person goes ahead and eats it, they consume it, break it down, cellular respiration occurs, they get the energy from that ice cream, and then they go ahead and they go bike riding and they use that energy. The amount of energy that we're putting in is the amount of energy that we are then able to take out or put out. If we look at this picture of the sun, that's that radiant energy, and we know that a tree or a plant could take that in, photosynthesize it, and it becomes chemical energy stored in the reserves of that plant to be used as it needs to grow and develop. We have chemical energy stored within gasoline that's used to make the car run. We have electrical energy for our thermal heater. Okay, and again, energy is always conserved. The amount you put in is the amount you are getting out. It doesn't magically disappear. It doesn't get used up per se, because energy cannot be created, nor can it be destroyed. And you know that. Okay, at the end of this, I'm going to put a sim in the details so you can go ahead and you can practice with skate park energy, with a skateboard and ramps, and see that the amount of energy, the potential energy, as it gets used, you'll see that no energy is getting lost. Okay. Now, when we talk about the conservation of mass, it's the same idea. Mass is not being created, nor is it being destroyed in a chemical reaction. It may look different, but the mass is the same. So, for example, if we were to look at our fire here, when you think about the wood that's being burned, when you think about the oxygen molecules that are being used to feed that fire, if you were to take that mass, and then once the fire was extinguished, if it was possible, to collect all the ash and kind of lasso all the carbon dioxide and other chemicals that have sort of blown away in the smoke, the mass before and after would be identical. Okay, it may have started as oxygen and now be carbon dioxide or burnt carbon. But the mass is identical. You're not destroying it. You're not creating it. It is absolutely identical. And I know you can show what you know about this particular example here. Let's look at our scale, and on our scale, we have a flask. Within the flask, we have a test tube. If we invert or tip that whole concoction over there, the chemical that's in the test tube will mix with the solution that's in the flask. Okay, we mix them up. The end product may look very different. According to our caption, we actually have a white precipitate, so we've got like some white powdery looking like stuff floating in the liquid. But if we started off with 300.23 grams, what should our end mass be after the reaction? And then my other question, if this was an exothermic reaction, okay, a reaction that gave off heat, where did that energy come from and where would it go? Show what you know. Good luck.